Okay. Hey everyone. So we today we are going to talk about how the light behaves in periodic structures. So if you think about like how our discussion has been progressed, was that like we began with the interaction with light with a small particle, right? And how light scatters off if it interacts with small particle. And then we started to talking about light propagation along a dielectric waveguide, right? So that how the light basically interact with a 1D structure. So in this section, I'd like to talk about the interaction of light with a periodic dielectric structure, which is called photonic crystals. So probably many of you already heard about the term photonic crystals, right? And probably also some of you knows about the basic properties of photonic crystals. Like photonic crystals can have photonic band gap, which can be used to create photonic cavity. But in this lecture, I'd like to focus more on understanding about the properties of photonic crystals, not just conveying, the characteristic aspects of photonic crystals, but try to give you a basic understanding of it. So so if you look at the atomic lattice, like if you look at how a solid material is composed, it's composed of periodically spaced atoms, right? So this figure here is the atomic lattice structure of boron nitride. So you can see there are two different atoms are placed and forming a honeycomb lattice. And then if you have this type of a lattice, you have a band structure, looks like this. Okay. And this is an electronic band structure. So this electronic band structure arises from the periodic placement of atoms. And here the same, like just using the same principle, if you place optical structures, like having a different dielectrics in 1D, alternating in 1D or 2D or 3D, we can create what is called photonic band structure, just like electronic band structure in solid, okay? And one good thing about these photonic crystals is that we can basically change the properties of lattice, like lattice spacing and the symmetry and material as we want. So we have a capability to engineer the photonic band structure as we want, basically. So the natural example of photonic crystal is the wing of morpho butterfly. So if you zoom up the surface of the wing of a morpho butterfly, it actually looks like this. It has some periodic structure. And then if you actually have this structure modeled in an optical simulation and try to shine a blue light, lambda equals 0.442 is blue light, you can see most of the light is reflected back and forming a kind of standing wave structure on top. Whereas if the incident lambda is 0.6 is green or yellow. Anyway, if a yellow-green color is shined, you can see most of the light is either transmitted or absorbed, right? So that if you look at the wing of the butterfly looks blue, and then because this optical property basically depends on the incidence angle, so that this butterfly actually looks a very fabulous color if you actually look at it. Like depending on the viewing angle, this color slightly changes, which looks very marvelous. And there are many examples. Like you can see the morpho butterfly, but there are many examples like a feather of a peacock or beetle, and some natural gemstones have their own microscopic structure, right? If you zoom up, like all these, the surface of these naturally occurring surfaces, you can see here they have some ordered structure, and the optical properties basically arise from this ordering. Okay, and you can see here, if you look at the size, characteristic length of this surface structure, you see here it is the scale bar, which is 1 micron, and here also these are just one. This is 1 micron, and here also the 1 micron. You can see the structures is on the order of micron or a little bit shorter than that, right? Which agrees with the wavelength of visible light, so that this structure have a specific color in visible spectrum. So that's enough for a very brief introduction about the photonic crystal. So in this lecture, I will basically follow this textbook. The textbook title is Photonic Crystals, Modeling the Flow of Light, written by John Ioannopoulos at MIT. And then one good thing about this book is it's free. So if you go to this website, you can download the PDF version of the book. And another good thing about this book is that this is very well written. So I think it's worth reading. So if you are not familiar with this stuff, I think this is very nice starting point. Okay, but at the same time, this book is a little too thick. So in this lecture, I'm going to just take some essence of the book and then try to align, those in a comprehensible manner. So if you have anything that you cannot understand from my lecture, I recommend you to take this textbook. Okay, so let me begin with the comparison between quantum mechanics and electrodynamics. And because because this is what is all about photonic crystal. So quantum mechanics, of course, the equation is Schrödinger equation, right? The governing equation is Schrödinger equation. And what we want to solve is the wave function psi, right? And then if you take the intensity or the magnitude of psi gives you the probability distribution function of an electron. And then in electrodynamics, what you solve for is, of course, the electric field and magnetic field, right? And then eigenvalue problem in quantum mechanics is Schrödinger equation. You can see the Hamiltonian operator is defined like this. And then in electrodynamics, the equation you solve for is wave equation, right? And then this our operator looks like this. And you probably are familiar with this relation, because when we solve for wave equation, the equation looked like this. Right? This is the equation that we solved for last time. And the only difference between this equation and that equation is that your actual this operator is written in this form instead of a Laplacian form, and that is because there is a possibility that your permittivity can depend on the spatial coordinate. So if your permittivity does not depend on spatial coordinate, then you can take this epsilon out. But if your permittivity is a function of spatial coordinate, you cannot do that. So I would say this is more general form, and this is kind of simplified form when epsilon is a constant. Okay. So here's one comparison. And now we want to think about the situation of having atomic lattice. So if you have an atomic lattice, so this is an atom, then because atom and electrons are attracting, if you think about their electric potential profile looks like this. So as electron basically wants to be attracted to atom, right? So this is how electron potential profile looks like. And that potential, the periodic potential, can be written in this form, like in VR. So VR here is the potential term. And then this VR is periodic with lattice vector R. And we can do the same thing. What corresponds to the potential in quantum mechanics, in electrodynamics, is permittivity. Okay, so instead of having a periodic potential, we can have a periodic permittivity distribution. So permittivity here is now periodic. And then another relationship is that if you have this type of translation operator, which I will explain later, this translation operator and the Hamiltonian are commuting, and also here too, which means the eigenvector or the eigenvalue, eigenvectors of this Hamiltonian actually share, these two operators shares the same eigenvector, right? That's what commutation means. And then what Bloch's theorem tells you is that if you have a periodic potential, your solution for the wave function must have this relation. So U of R is periodic function. So U of R is same as U of R plus R. Okay, which means this is a periodic function multiplied by e to the ikr. So if you have a periodic potential, your solution must have this form. That's Bloch theorem. And here the same. If you have a periodically alternating permittivity, then your electric field and magnetic field should satisfy this form, e to the ikr times periodic function. Okay, so that's called Bloch's theorem. So before I proceed, how many of you are familiar with Bloch's theorem? Can you raise your hand? How many of you are familiar with Bloch's theorem? Okay, Thomas and Kang Yong-min, only 2? 3? Okay, Kim Chae-yoon. Okay. Okay, so not that many people. So let me just try to explain you one more time. For those who are already familiar with this, you can just don't need to pay too much attention. So the Bloch's theorem, let me repeat the Bloch's theorem. So here, our setting is that we have epsilon of R, okay, permittivity function, permittivity as a function of spatial coordinate. And then T of R is the lattice translation operator. So what that means is that we, what this one does is if there is R, then if we apply this operator, we change R to R plus R, okay? And this large R is lattice vector, this vector, or this vector, like lattice, what basically defines the lattice spacing. And then, so this is basically definition. So if you apply the lattice translation vector TR to epsilon R, this becomes epsilon R plus R. Okay, and in this example, of course, this lattice vector is a linear integer multiplication of A. A is the spacing between two peaks here and Y direction, right? So this is basically lattice vector, what defines the lattice. So what is lattice translational symmetry? So here we have these functions. Okay, so let's try to do. Okay, so you have theta H. So theta here was the Hamiltonian, and then H is an electromagnetic field. So if you apply TR, that means we want to translate the spatial coordinate of both of these by vector capital R. So if we do this, then theta of R plus R and H of R plus R, right? And then because we know that theta is simply curl of this epsilon R, this is our theta as we learned before. And then we know that epsilon R is epsilon R plus R. And then this curl only applies for small r. So theta R and theta R plus R are identical. So we can go from here to there. And now if you look at this equation, then this is just a theta TR H, right? I mean, what I mean by H is H of R. So if you compare this side and that side, TR and theta TR are same. So if you switch the order of this linear operator, they are the same, which is called they are commute. So theta and TR are commute. If the two linear operators are commute, they have common eigenstates. That's what's known from the linear algebra. So now we have equation that we want to solve, right? So this equation is again electrodynamic wave equation, as we learned here, right? Eigenvalue from here. And then another thing, the second equation is this. So here, if we apply TR to H is again electromagnetic field, then this should satisfy a certain eigen equation. So this is C of R is the eigenvalue and H is the eigenvector. Okay, so and then they share the common eigenstates, common H. And then what we are gonna do is that we first focus on this equation, okay, and then we apply this property. So TR and TR prime, let's think about it. TR prime changes R to what? R plus R prime, right? This is translation operator. And then if you apply TR to this, to this, that gives you R plus R prime plus R, right? So consecutive operation of TR prime and TR is equal to T of R plus R prime. right? This is just a translation. You can basically add two translational operator into a one translation operator. So which means, and then you apply this to that equation. That means the eigenvalue of CR, and then eigenvalue of TR, which is CR, and then eigenvalue of TR prime, which is CR prime. If you take the product of these two, this must be equal to the eigenvalue of TR plus R prime. Okay, so what I'm telling you is that if you take a product of two eigenvalue, it becomes the eigenvalue of some of these, variable, which is the property of exponential function. Okay, so what I'm saying is that exponential A plus B is exponential A exponential B, right? So if some function have these properties, we can say that this function is exponential. Okay, and then if it's exponential, there's no problem writing it this way, e to the I k dot r. Then somebody may question like, okay, why I? Well, there's no need that we need to have I, but there's nothing prevent us to have I here. So we can just set it because it's convenient. And now what we know is here h of r plus r, which is coming from here, is e to the ikr, which is cr, hr, right? And then this is just one form of Bloch's theorem. And the second equation is another form of Bloch's theorem. They are equivalent. So second form, let's look at the first form and second form. Second form is like saying that the solution, your solution in the periodic potential profile must be the product of e to the I k dot r times ur, but this ur should be periodic. Okay, now from 2 to 1 is easy. You can just plug this in to this equation and then plug this equation also to this equation. So if you do that, let's say, let's do it for this one, then e to the I k r plus r, u r plus r. And then if you plug this equation to this one, is equal to e to the I k dot r, e to the I k r, u r. So if you compare the front part, they are the same. And the second part are also the same because u is periodic. So from 2 to 1 is easy, right? And then from 1 to 2, the way you prove it is you want to divide this into you can just take e to the I k r is equal to e to the I k r plus r multiplied by minus e to the I k r. Okay, so this and that are same. And then move this term to that side. Then what happens is e to the minus I k r plus r, h r plus r is equal to e to the minus I k small r hr, right? And then what you realize is that if you define this as your ur, then this one is ur plus r, right? And then from this relation, your HR is equal to e to the IKR UR, which is the second part of the equation. Okay, so I'm not sure whether this derivation was clear enough, but anyway, you kind of see what's going on, right? So I tried to explain you that if there is a certain periodicity in the system, basically your epsilon have a periodic property, then your wave solution should also satisfy certain periodic relation. But this periodic relation is not as simple as this. It's not like this simple, right? But it's more like this, right? So these equations are your solutions are periodic function multiplied by e to the IKR. So that's the solution of Bloch's theorem. Okay. Now, by the way, if you have any question, you can just type in, and then I'll come back to answer those. So I'd like to talk a little bit more about the lattice itself. So I'm going to tell you about the concept of Bravais lattice. So Bravais lattice is an infinite array generated by a set of translation operations described by this. Okay, so let me tell you this. So here is the example of 2D Bravais lattice. Okay, and this Bravais lattice, for instance, the square lattice can be generated by these two basis vectors or primitive vectors. Okay, so A1 is along y direction, A2 is along x direction, and then any linear combination of these basis vectors multiplied by some integer number can define lattice point. So for instance, this one is what? 2A1 plus 2A2, right? And so on. So if you have primitive lattice, then this any linear multiplication and then superposition of these vectors gives you the lattice point. And there are, and then considering symmetry, there are only 5 types of Bravais lattice are possible in 2D. And then only 14 Bravais lattices are possible in 3D. And then some of you may ask, okay, then what's the difference between square lattice and rectangular lattice? They look the same. Well, the difference is that square lattice, the lattice vector, the lengths of the lattice vector are same. Rectangular lattice, the lengths are different. Then why does this matter? Because that affects the symmetry. For instance, square lattice satisfies C4 symmetry. What do you mean by C4 symmetry? Is if you rotate the things by 90 degrees, they are the same, right? Whereas in rectangular case, there is only C2 symmetry, right? C4 is not allowed because if you take a 90-degree rotation, you can immediately notice things has been changed. So the way we define grouping basically the lattice or crystalline structure is based on symmetry operations. Like what kind of a symmetry is preserved in different types of lattices. So here's one quick quiz. Look, probably everyone knows about, not everyone, but many of you are familiar with graphene. Okay, so graphene have this type of a honeycomb lattice. And then honeycomb lattice, and then you have C, all these atoms are carbons. So do you think honeycomb lattice is a Bravais lattice? Can anyone answer to this question? Like, do you think the graphene lattice, the honeycomb lattice, satisfy the Bravais lattice condition? Maybe not, right? Why not? Because if you have a primitive vector, vector 1, vector 2, then you can immediately notice that there should be a lattice point here, right? That is missing. So that honeycomb lattice itself is not a Bravais lattice, right? In order to be a Bravais lattice, it has to be hexagonal lattice. But honeycomb lattice, this atom is missing. So in order to define a graphene lattice structure, what we do is we combine these two as one unit, and then this unit actually forms a hexagonal lattice. If you think about it, like this unit and that unit and that unit, here's multiple units, and then this and that vector, this vector and that vector, basically the primitive vectors of honeycomb lattice, right? And these two units, these units are repeated in hexagonal lattice. But anyway, that's the concept of Bravais lattice. And now we want to talk about its reciprocal space. So let's move on one slide. And this is a reciprocal space. So the reciprocal lattice is defined in this way: the set of all vector G that satisfy e to the I GR equals 1. And then here, R is Bravais lattice vector. So you can actually find the closed form of G, the reciprocal lattice primitive vector. So primitive vectors of the reciprocal lattice B1, B2, B3 can be obtained by using this following equation. So for instance, if you have a real space lattice, Bravais lattice, having A and A basis vectors, in the reciprocal space, you have also another lattice with basis vectors G1 and G2 can be obtained from these equations. Okay, and then of course you can see this relation E, I, G, R. So R and G are basically Fourier pairs. So you can understand the reciprocal space A is as a Fourier transformed space of the real space. Okay, so sometimes we call this as a real space, and this space as a K space. K is a wave vector space. Okay, so here are the basically, I'm just giving you the definitions, like how people try to define lattice and reciprocal lattice, and try to give you some useful terms. And another thing that you need to define is what is called Brillouin zone. So I have a relatively long definition, but what I would like to say is that the Brillouin zone is defined in K space. Okay, so as I said, if you have a lattice in Bravais lattice in real space, you have a reciprocal space, and then also reciprocal lattice points. So Bravais lattice is basically the area or the volume that each point in reciprocal space covers. So let me tell you how to find it. So let's say if you Fourier transform this, you get the reciprocal space. And then here, the blue dots are reciprocal space vectors, reciprocal space points. And then if you want to define how much area is covered by this dot, what you want to do is you basically try to draw a line between its neighbor, and then cut it into half, and then saying that, okay, then this region is correspond to this dot, and then that region correspond to that dot, and then you do the same thing for all the neighbors, first neighbor and second neighbor. Then you realize that this yellow region is where it is basically correspond to this dot, and then you can see that you can if with this square you can tile the entire K-space. This is called Bravais lattice. And similarly here, if you have a hexagonal lattice, you also have a reciprocal lattice, which is also hexagonal. And then in this case, you have 6 nearest neighbors. And then also doing the same thing, draw a line, cut into half, draw a line, cut into half. Then you realize that your Brillouin zone has a hexagonal shape, right? And you can also do the same thing for the 3D lattice, like this. If you have a FCC face-centered cubic structure, then each of your reciprocal lattice point, which is called gamma point, have and then your Brillouin zone looks like this. Okay, it's a little more complicated, but anyway, the idea is the same. And then people tries to define basically giving a name to the important high symmetry point. For instance, the origin k equals 0 is always called gamma point. Okay, so if somebody say you gamma point, that means k equals 0. And then k point, w point, x point, u point, l point. This is not just random names. This is always have this name. So like if you can see, and also k, w, x, u, l have all important symmetries, right? So for instance, k is the midpoint of this. If you look at k is just the midpoint of this line, and then w is a corner, and then x is midpoint of this surface, and u again is the midpoint of this edge. So these high symmetry point has their own name, okay? But you don't need to memorize those though. But what's useful is gamma. Gamma is always used for 0 k vector. Okay, so now we are ready to understand the photonic crystal. So let's begin with the simplest form of photonic crystal, which is 1D alternating permittivity layer. So here, what we want to consider is we have 2 dielectrics, green and blue, having different epsilon. And then they are alternating with periodic manner. So the period is A in this case. And of course, the portion of blue material and green material inside a period is also fixed, but it can be changed. So primitive lattice vector in this case is AZ, right? This is also Bravais lattice, 1D Bravais lattice. And then primitive lattice vector in this case is AZ. And then any integer multiple of this vector tells you about the lattice point. And then primitive reciprocal lattice vector is, of course, also can be easily found from the previous equation, which is 2 pi over a actually along z direction. Okay, so for Again, if you draw, so this is G direction. So G direction, primitive lattice vectors is A, Z. And then if you go to the K space, then the reciprocal lattice vector is 2 pi over A. And then if you think about the Brillouin zone, of course, is the midpoint to the nearest neighbors. So if you take the midpoint, and this is 0, say, then it's from minus pi over A to pi over A, right? That's the Brillouin zone. In this case, Brillouin zone is just a line. It's not even an area because it's 1D. Now, if you apply the Bloch theorem, in this case, electric field of R plus AZ is, this is R. Then this is like e to the IKZA times e to the E of R, or you can also use the second form. The second form is ER is equal to e to the IKR UR, and then here e to the IKR can be separated into two. So K parallel is the surface parallel vector, and KZ is just KZ vector. So you just wrote e to the IKR into two product of these two terms, and then U of Z is of course the periodic function, right? So the periodicity is A. Okay, so that's Bloch's theorem. So how do we solve this problem? Well, we know it's going to satisfy the Bloch's theorem. The solution should satisfy the Bloch's theorem, but that's not the end of the story, right? In order to know how actually your electric field and magnetic field is going to look like, you need to be able to solve this. How to solve this? You're going to use transfer matrix. Okay, so let's learn about transfer matrix. Transfer matrix connects the electric field amplitude of one side of a layer to the other side of the layer. So if you apply, this M matrix, transfer matrix, multiply this matrix with a vector whose elements are the E1 plus, which is the incoming wave from the left side. And then E1 minus is outgoing wave to the left side. And similarly, E2 plus is outgoing wave to the right side. And then E2 minus is incoming wave from right side. So M matrix connects these components. And what we do know is that, let's say we want to know about E2 plus, for instance. Okay, so in order to have E2, E1 minus is irrelevant, right? Because it's outgoing wave, so there's nothing. So if you think about like how to create E2, you should have transmitted portion. You should add transmitted portion of E1 wave and the reflected portion of E2 minus wave, right? So transmitted portion of E1 plus wave, and then reflected portion of E2 minus wave. So here, T1, 2 means transmission from 1 to 2. Okay, from transmission from 1 to 2. And this one is reflection from 2 to 1. So what I mean by 2 to 1 is that, so this subscript, so this subscript defines the side. So this side is 1, that side is 2. So T1, 2 is from here to there. R21 is the case where the input beam is coming from 2 to 1, okay? And then R means reflected. So R21 is the reflected portion of E2 minus wave. And similarly, in order to get E1 minus, you need to take into account the reflection of E1 plus mode. So R12, E1 plus, and also T21 of E2 minus, right? So these two equations, rearrange, you get the transfer matrix. So one problem about this this equation is that, here E2 plus, here's E1 minus. So it's not arranged the way we want. So what we want is we want E1 plus and E1 minus on one side and E2 plus and E2 minus on the other side. So if you rearrange the term, you get the matrix, the transfer matrix. Okay, so what's the beauty about the transfer matrix is that now with the transfer matrix, you can find the relation between one side to the other of a layer. So if you have a multiple layer, all you need to do is just multiply matrices, because say M1 connects this and this. M2 then connects this and that side, and so on. So in order to see the overall response of the entire structure, you can just multiply those, right? So the question is now how to find the transfer matrix of our structure, right? So to answer that question, we need to look at this. So we want to consider two cases. First case is the propagation through a homogeneous medium. So let me remind you that our transfer matrix connects E1 plus and E1 minus to E2 plus and E2 minus. And now let's think about, we define, okay, this is our area of interest, okay? And then we want to find the transfer matrix of this area. Then what's gonna happen? So what's important here is that there's nothing, nothing changes. It's like homogeneous media, but we just set a artificial length of our the area of our interest, D. So what happens is that in this case, let's think about E1 plus. E1 plus, let's say this is the E1 plus, then E1 plus should go propagate without any reflection, of course, and should be connected to E2 plus. I'm sorry, E2 plus. Is that E2 plus? And let me check. Yeah, E1, yeah. E1 plus becomes E2 plus. So the only difference here is that the phase difference. So because E1 plus is the electric field measured at this point, and E2 plus is electric field measured at that point, this specific position. So there is a distance. So there is a phase advance associated with the distance. So exponential e to the I k dot d is the phase advance. And in this case, k is n omega divided by c. So psi is equal to phi is equal to n omega c d, right? And similarly, and of course, this term, which connects E1 minus to E2 plus is 0 because there's no reflection or anything. So it must be 0. And similarly, if you think about the relation between E2 minus and E1 minus, so in this case, E1 minus is this propagating in that way. So what's actually happening is E2 minus is coming in, propagates, and then becomes E1 minus. So the phase is actually, because these two waves are going in opposite direction, the phase advance is also in the opposite direction. So it's the same amount of phase shift, but in opposite direction. So this is the propagation transfer matrix. Okay. Now, let's think about the second case. Second case is we set our area of interest as 0 thickness. But the difference is that we are talking about the boundary between two medium, N1 and N2. Okay. And here, of course, not only the transmission, but also the reflection happens. And here too, not only the transmission, but also the reflection happens. So it's reasonable that all four components are non-zero. But good thing about this point is that there's no phase advance. So all we need to know is just the Fresnel equation, right? What determines the transmission and reflection of a wave at a material boundary. The Fresnel equation, I forgot what it was like, but it's like N1, T1 is N1 plus N2, N1 minus N, so something like this, okay? So if you have a transmission and reflection coefficients at the boundary, then you can immediately translate that into a transfer matrix. And that has this form if you actually carefully look at it. So now you have these two components. You can do everything about 1D photonic crystal. Because now we want to know, the third is just adding these two. Now our area of interest or region of interest is this. Okay, one of the boundary is actually material boundary. The other boundary is not a material boundary, but just we set it as a big, just a arbitrary length d. In order to find the transfer matrix of this region, what we need to do is multiply these two, right? I12, P1. So P1 is the propagation matrix. And then I12 means the interface matrix. So propagation and interface multiplied gives you the overall response. And then we can easily do it, right? So if you imagine to solve this problem, like, from the zero base, it's a little bit more complicated, but because we already solved for propagation and boundary separately, all we need to do is just to combine the partial solutions. So what's next? We can just keep doing that. So what we want to do now is we have now N1, N2, N1, N2, this case. So in this case, our boundary, our area of interest, region of interest is this. And then here, we begin with transmission because it really depends on, so let's say this propagation, interface, propagation, and interface. Let's say these are our area. And of course, that interface probably corresponds to the previous segment. So what we need to take into account is the propagation interface, propagation interface. So propagation in P1, interface of 1, 2, propagation in medium 2, interface of 2, 1, right? And that gives you the transfer matrix of our one unit, right? So we can easily do this. And then what we can do is apply Bloch's theorem, right? So this is one equation that we know from transfer matrix formalism. But now if you think about, let's say you define this as E of R, then this becomes E of R plus AZ, right? Because this is the one, basically one lattice spacing. So, and Bloch's theorem tells you that this part and that part should be connected by this, right? That's what we know from Bloch's theorem. So if we write this into a matrix equation, this looks like that. So now we have two equations. One gives you the relation between, the electric field in one side and electric field in the other side. And then a second equation is from Bloch's theorem, right? And now the eigenvalue problem gives you that this must be, so in the eigensolution have this property, like these should be the same, equating basically these two. And then you have m of e m1 m, m plus m minus is e to the I kga e m plus m minus, right? And then rearranging the term, this is m, the matrix, and then e to the I kga is a scalar, so you multiply the identity matrix, and then em plus em minus is 1. So in order to have non-trivial solution, like trivial solution is of course e, both of e are 0, then this is 0. In order to have a non-trivial solution, the determinant of this equation has to be 0, right? And from that, we can get this relation, okay? So that is basically the dispersion relation of periodically arranged 1D photonic crystal. Okay, so you can kind of see how these all these things are coming from. So cosine A kg probably is coming from here, right? There's a kg and a, so there's something related with cosine. And also, if you think about M matrix have all these R1, 2, N1, 2, and and then T1, 2 stuff, so that you can easily imagine that if you combine these and take the determinant, you get sort of this type of an equation, right? So I just recommend you to try this by yourself. Okay, you can just try this. So you get the dispersion relation. Now, you draw the dispersion relation for the case where D1 is equal to D2. Okay, so the portion of blue material and portion of green material are exactly the same. So it's A over 2, A over 2. And then when these two materials are having the same permittivity, basically they are the same material, then if you draw the dispersion relation in a Brillouin zone, it looks like this. Okay, so the reason why we are drawing things only in a Brillouin zone is because these relation is repeated in every 2 pi over a. So we don't need to draw like the entire K space. We only need to draw things in a Brillouin zone, and that's enough. So if you draw it, it looks like this. Okay, so you can imagine this as this. If you have, so there's nothing, right? If there's nothing, this is just one material. There's no difference between two material. So this is just one material. And if you have only one material, you can imagine your dispersion relation should be what? K is equal to N omega C, right? So if you draw K and omega, it's just a linear equation. And of course, K has 2 directions. So if you draw it in this way, it's gonna be just doing this, right? It's a free space dispersion relation. But because we set our periodicity as A, so this is our Brillouin zone, right? So what's happening is that same thing is repeated in every 2 pi over a. So this is effectively like gives you this line and that line and so on and so on and so forth. Okay, so this is how your photonic band structure looks like when there is no difference, like epsilon and epsilon 2 are the same, basically the free material. But now, if you change the epsilon 2 a little bit to epsilon 2 equals 12, then strange thing happens. At the zone boundary here, there's appears the region where there is no state, no propagating state for a certain range of frequency, which is called photonic band gap. Okay, and here too, photonic band gap appears. And then this tendency becomes more significant if we change epsilon 2 becomes 1. So the index contrast becomes higher, then the band gap becomes huge, right? So what I mean by band gap is that there's no propagating mode within this omega range, frequency range. So what happens is that if you have this crystal, is epsilon 1, epsilon 2, epsilon 1, epsilon 2, and then shine the incident wave within this frequency range, because there's no propagating mode, it's going to be reflected 100%. Okay. And if we shine this frequency, then of course there's a solution, right? So that the wave can penetrate with certain properties defined by this dispersion relation. Okay, so to understand better how what's happening like at this point, where the band gap occurs, like to this point, we make an index of this band to be n equals 1 and this to be n equals 2. So you can kind of consider this as a sort of a valence band, and then this as a conduction band in a solid state system. So what's happening, if you look at this, is this, just these two cases. So epsilon 1, epsilon 2, when the epsilon 1 and epsilon 2 are very similar, and when epsilon 1 and epsilon 2 are very different. So for the band 1, the lower band, you can see here, if you look at the electric field profile, large amplitude appears at high index medium when epsilon is high. And here too, if you look at this, at lower band, high epsilon band has field maximum. And then the upper band, if you look at the upper band, the electric field profile is the other way around. Most of the electric field is in the low index medium. Okay, so how to understand this? Well, I recommend you to make some analogy here. So, it's not a, how can I say, rigorous analogy, but you can compare the quantum mechanics and electrodynamics. So in quantum mechanics, again, like you have some, can I say, kinetic energy term plus potential energy. And then in our case, we have epsilon, 1 over epsilon. And because it's 1 over epsilon, you can kind of think that small potential corresponds to high epsilon. Okay, small potential corresponds to high epsilon. So how does this analogy works? Let's look at this. So let's say you have an atoms here. And then if you have an atom, as I said, your potential profile looks like this, right? Electrons tend to be attracted to the atomic sites. And then in the electronic system, you have a valence band and conduction band, right? Valence band, electrons are localized to around the lattice points, around the atoms, right? So you can see here in the valence band, if you think about the electron probability distribution, they tend to localize at the low potential energy, right? Whereas the free electrons tends to be in the free space, right? It tends to go like in free space. So and the free space, of course, has high potential energy compared to the lattice point. So the in conduction band tends to go to the high VR, right? And similar thing happens here. In the lower band, photons tend to localize at high index medium because that's more energetically favorable. Okay, and the upper band tends to be at high energy. So in the free space basically, and or lower permittivity region. Okay, and then another thing that I want you to know is that the mode, this electric field profile should be orthogonal. So the electric mode at the lower band and electric mode at upper band should be orthogonal, which means if you take the overlap integral, they shouldn't be any much of an overlap. So you can see here, if they are peak at different position, their overlap integral vanishes. So that's why also it has different forms. Okay. And now, if you look at the in terms of energy, you can see the most of the energy in this case, like the upper case, the band 1, the lower band, resides in the high index medium, right? Which makes your frequency lower, eigenfrequency lower. And then on the other hand, this case, here you can see there's no negligible amount of energy resides in the low index medium, which makes this mode to have a higher, relatively higher compared to this guy, relatively higher frequency. So that's why we have a band gap, photonic band gap. Yeah. So yes, I think I'd better stop here and probably take a few questions, and I'll proceed in the next lecture. So if you have any question, please ask. I guess this was pretty easy, right? I mean, it's not like super easy, but at least it's, how can I say, comprehensible. Like if you follow the procedure step by step, you can get the conclusion where you have a photonic band gap in 1D crystal. And basically, it's getting more and more complicated. But the basic procedure for having a photonic band structure for 2D or 3D photonic crystals is the same. It's exactly the same. It's just more complicated and involves like vector calculation. So it's all about matrix diagonalization. Like once you get to the point, and the only thing left is matrix diagonalization. Any question? Okay, Chang Min-soo asks, slide 14. Oh, yes, N1 and N2 are repeated, as we said. Like what we want to solve is the figure in the slide 11, where N1 and N2 are repeated with periodicity A. So in order to solve this problem, I introduced this transfer matrix method. And so, yeah, and then we get up to this point.